Hey guys, in this video we'll be solving a two-dimensional momentum problem. This involves all of the same principles of a one-dimensional momentum problem, for example, conservation of momentum. Hey guys, in this video we'll be solving a two-dimensional momentum problem. This involves all of the same principles as a one-dimensional momentum problem, such as conservation of momentum, but things get quite more involved. If you want to start out with the basics, check out the introductory video on momentum exercises. In this particular video, we're going to calculate how to avoid a comet colliding with the Earth by deflecting its trajectory over a couple of angles. So it's a basic scattering problem. And as always, if you have any questions along the way, feel free to ask them in the comments down below. And with that said, let's get right into it. Let's consider the following scenario. We have a very heavy object, for example a comet, with a gigantic mass of, let's say, 100 gigatons or 100 billion tons. And this comet is hurling towards the Earth with a massive velocity of 20,000 kilometers per hour. And if we would do nothing at all, then it would crash straight into the Earth, which is a situation that we obviously want to avoid. And to prevent this catastrophe, humanity came up with a plan to launch another object into space in order to collide with the comet before it reaches the Earth and thereby deflecting its trajectory. Now, the mass of this object that we send into space is obviously restricted by what we can launch. And sadly, the heaviest mass that we can launch is 0.1 gigatons, or only 0.1% of the mass of our comet. And we've made our launching calculations such that the angle with which our small object will collide with the comet is roughly 60 degrees. Now, as you can imagine, this collision will deflect the comet and put it on another trajectory. And in order to just miss the Earth, it needs to be deflected by an angle of at least 3 degrees. Now, you probably notice that there is one parameter missing, namely the velocity of our small object that we're launching to collide with the comet. And this is exactly what we are going to look for. Namely, what velocity do we need to give this object in order to get this 3 degrees deflection? And that is exactly what we'll be doing in this exercise. And as you can clearly see, this is a two-dimensional problem involving scattering objects, and therefore a two-dimensional momentum exercise. And to solve this exercise, we are going to rely on the fundamental principle of conservation of momentum, which basically says that in a system, the total momentum of the system will be conserved throughout time. So if we take two separate cases of the system and we calculate the total momentum, which is the sum of all of the momentum of the individual particles, then this total momentum will be equal for both cases. So how does this work in two dimensions? Well, in two dimensions, it turns out that the conservation of momentum holds in each dimension, namely in the x direction and in the y direction. So we basically get two distinct and independent equations expressing conservation of momentum. And writing this out, this looks as follows. In the x direction, we have the total momentum in the x direction in situation 1, for example, the case before the collision, which has to be equal to the total momentum in the x direction after the collision, so with a superscript 2. And the same holds in the y direction. The total momentum in the y direction before the collision will have to be the same as the total momentum in the y direction after the collision. And this basically gives us two separate equations that we now can use to solve this problem. If we, for example, look at the two scenarios where the first one is before the collision and the second one is after the collision. And so what we are left to do is to first calculate the total momentum before the collision of the system, which is the momentum of the comet plus the momentum of the smaller object, and then afterwards calculate the total momentum after the collision, and then compare both and put them equal to each other. So let's do that right now. So first, let's calculate the total momentum in both the x and the y direction before the collision has taken place. And to do this, we need to go back to our original sketch and define an x and y direction. And let's take the most obvious way which is that the x direction is simply in the direction that the comet has towards the Earth. So this will be the x-axis, and the y direction will simply be perpendicular to it. So it will be this axis, the y-axis. And this immediately shows us that the comet before the collision only has a momentum component in the x direction, since it's only moving in the x direction. And its y component will be 0. Now, for this small object that we are launching into space to collide with the comet, we see that things are a bit more tricky. This 60 degrees of angle of inclination makes it such that we have both a momentum in the y direction and in the negative x direction. And this is what we will have to take into account. So let's go and write this down. First, in the x direction, we have the following. We have that the total momentum, which is of course p, which is equal to m times v, so the mass multiplied by its velocity. For the comet, which I will color code in blue, we have the mass of the comet multiplied by the velocity of the comet. And that's basically it, because we know, as we said previously, that the comet only travels in the x direction. Then we add to this, of course, the x component of the object that we are launching. Well, this of course will be the mass of our smaller object multiplied by the velocity of our smaller object multiplied by a factor that takes into account this 60 degree of angle of inclination. And to find this, let's go back to our original sketch and see what it actually is. Given that this angle of inclination is 60 degrees, then we see that in the x direction, it will be this projected distance right here. And if we turn this triangle upside down, then we see that this will be the cosine of 60 degrees. So that means that this factor to take this into account will simply be the cosine of 60 degrees. And at this point, we will still leave it as the cosine of 60 degrees, just to be able to, in our final result, see where which term really comes from. And the sum of these two terms, to remind ourselves, will be equal to the total momentum in the x direction before the collision. Now in the y direction, things are of course very similar, with of course the added simplicity that the momentum of our comet in the y direction before the collision is simply 0, because it is moving in the x direction. Now we add to this the y component of our object that we launched. Now this will of course again be m times v multiplied by a factor that takes into account that we have this angle of inclination. Well, and if we go back to our original sketch, we see that we now do not need this projected distance, which was the x projection, but at this point we need this projected distance. And using trigonometry, we know that this will be the sine of 60 degrees. Therefore, we can simply fill this in to get the sine of 60 degrees. And then of course, this will be the total momentum in the y direction before the collision. And we're already halfway done. Because at this point we already have one piece of the puzzle right here. These two total momenta in the x and y direction before the collision. And what we're left to do now is of course to look at the situation after the collision. And for the situation after the collision, we make another assumption. When these two objects collide, they will stick to each other. Such as, for example, two balls of clay. When they collide, they effectively become one ball of clay. And then, of course, the mass of this new object will simply be the mass of our original comet plus the mass of the smaller object that we sent into it. So what this means is that at this point, we basically have one object that is composed of the two original objects and that is moving in one direction. And to go back to our original sketch, and it will be this new object that will be traveling in this deflected trajectory with an angle compared with the x-axis of 3 degrees. And just to remind ourselves what we're doing, it is exactly this trajectory for which we need to find the initial velocity of our smaller object for. And at this point, of course, we need to find again the x and the y component of the total momentum of the system. But in this case, the system is only this one object, where before it was the sum of these two objects. Now it's just one, so it simplifies a bit. Again, we need to find the x and the y component. So we need to project the momentum that it has, so m times v, onto the x-axis and onto the y-axis. And since we see that it makes an angle of 3 degrees with the x-axis, the x and y component simply becomes the cosine component and the sine component respectively. So let's write this down. We have in the x direction the total momentum, so the total mass, which is the sum of the masses of our two original objects, multiplied by the velocity that this composite object has. But we're looking in the x direction, so we have to multiply it with the cosine of 3 degrees. And this will then represent the total momentum in the x direction of situation 2 after the collision. In the y direction, things are very similar. We have again m multiplied by v, so the mass of the composite object multiplied with its velocity. But now we need the y component, so we multiply with the sine of 3 degrees. And this will simply be the total momentum in the y direction after the collision. And it is at this point that we can use conservation of momentum. And because we're working in 2 dimensions, we will get 2 equations of conservation of momentum. Namely, the first one is the total momentum in the x direction before the collision is equal to the total momentum in the x direction after the collision. And likewise, we have the total momentum in the y direction before the collision, which is equal to the total momentum in the y direction after the collision. So these are 2 equations. And for all 4 of these quantities, we have expressions with all of the system properties. And of course, also with our small v, which we are actually looking for. So let's first look at in the x direction. In the x direction before the collision, we had the mass multiplied by the velocity of the comet before the collision, plus the mass of our smaller object multiplied by its velocity, multiplied by this factor, the cosine of 60 degrees, which took into account the angle of inclination. And after the collision, we found the following, which is basically this term right here. We had the mass of the composite system multiplied by its velocity, multiplied by this cosine of 3 degrees. And similarly, in the y direction, before the collision, we had 0 for the comet, plus the mass times the velocity of the smaller object, multiplied by the sine of 60 degrees. And this now, due to conservation of energy in the y direction, has to be equal to m times v, basically this term, multiplied by the sine of 3 degrees. And here we now have it. We have 2 equations which involve this parameter right here that we actually want to solve. And let's see what quantities we do know. We know the mass of the comet, which was 100 gigatons. We know the velocity of the comet, which was roughly 20,000 kilometers per hour. The mass of the object that we launched into space, we also know it was 0.1% of the mass of the comet. This is just a number. This is also just a number. This mass is simply the sum of both masses of our comet and our object. And the only thing that's also an unknown is this velocity of the composite object right here. But we see that in the second equation, this is also true. This will be the only variable that we don't know. So we see that we have 2 unknowns, namely the velocity of our object and the velocity of the composite object. But we also have 2 equations. So this should turn out perfectly. So let's just solve this set of 2 equations. And if you're unfamiliar of how to do so, I gladly refer you to my other video where we focus specifically on solving sets of 2 equations. Let's call this equation 1, and let's call this second equation, well, fittingly equation 2. Let's first take equation 2 and rewrite it such that we have this v on one side of the equality sign. And since this term is just 0, this is quite straightforward. Just take this mass and this sine of 3 and put it on the other side of the equality sign. This gives us that v, the velocity of our composite object, is simply equal to the mass of our launched small object multiplied by its velocity, multiplied by the sine of 60 degrees. And then we, of course, divide this by the other things, which is the mass of the composite object multiplied by the sine of 3 degrees. And we see that we have now found an expression for the velocity of our composite object after the collision, which we can now use to fill in our first equation, such that we only have one unknown in our first equation, namely the thing that we're trying to find. So let's take again our first equation, which was the mass of our comet multiplied by its velocity, plus the mass of our small object multiplied by its velocity multiplied by the cosine of 60 degrees, which was the angle of inclination, which is equal to the mass of the composite object after the collision multiplied by its velocity. And there we simply fill in what we just found. We found the mass of our object multiplied by its velocity multiplied by the sine of 60 degrees, which we then divide by the mass of our composite object multiplied by the sine of 3 degrees. And of course, we should not forget this term right here. So we multiply with the cosine of 3 degrees. And apart from these two masses cancelling each other out, let's see what we actually have in this equation and if we did indeed succeed in what we set out to do. So which quantities do we know? We know the mass of the comet, we know the velocity of the comet, we know the mass of the object that we're shooting at this comet. The cosine of 60 degrees is just a number. The mass we know, this is a number, this is a number, and this is a number. And we see that indeed we only have one variable that we don't know, the velocity of the object that we're shooting at the comet, which is exactly what we were set out to find. So we can rearrange this equation such that this red v is on one side of the equality sign and all of the rest is on the other side. So we find m times v times the cosine of 60 degrees minus m times v times the sine of 60 degrees multiplied by the cotangent of 3 degrees. And what I did here was simply move this term to the other side of the equality sign, so we get a minus sign, and divide this cosine of an angle divided by a sine of an angle, and this will always be the cotangent of this angle. And this will be equal to simply moving this term to the other side, so getting a minus sign. So this will be equal to minus the mass of the comet multiplied by its velocity. Factoring out this v from these two terms, we get the following. We have the velocity of our object that we're sending to the comet multiplied by its mass times the cosine of 60 degrees minus its mass times the sine of 60 degrees multiplied with this cotangent of 3 degrees. And again, this will have to be equal to minus capital M times V. And of course, we see that this bracket right here, we can divide away and thereby get to the other side of the equality sign. And then we have isolated this small v. So let's do that right now. We have that the velocity of the object that we're hurling at this comet is equal to minus the mass of the comet multiplied by its velocity divided by the mass of the comet multiplied by the cosine of 60 degrees minus the mass of the comet multiplied by the sine of 60 degrees multiplied by the cotangent of 3 degrees. And we can write this a little bit more neatly, getting rid of this minus sign and swapping it right here and factoring out this mass of our object that we're launching out of these two terms, we get the following. We get the mass of the comet multiplied by its velocity divided by the mass of our object that we're sending multiplied by the following, just all numbers, the sine of 60 degrees times the cotangent of 3 degrees minus the cosine of 60 degrees. And this is now our final result for the velocity that is needed for this object that we launch into space, such that the comet is deflected by at least 3 degrees. And let's make some checks to see whether we made any mistakes. And a check that is always good to do is to look at the units of your solution. On the left-hand side, we have a velocity, and therefore we expect the units of velocity on the right-hand side. We see that all of these terms right here are just numbers, the cosine or the sine of angles. we see that we have a mass in the numerator and the denominator, so their units check out, and the only thing that we're left with is indeed a velocity. So the units do indeed check out. And doing this units check, we also see that we basically have a velocity which is equal to another velocity, or more specifically, the velocity of our object needs to be a specific factor multiplied by the velocity of our comet. And this factor is basically this thing right here, everything except our velocity. Now, if you plug in the numbers, you find that this factor in front is roughly 63 times. So we know that our velocity of our object will need to be 63 times the velocity of our comet. And since we know that the velocity of our comet was roughly 20,000 kilometers per hour, we find that the velocity of the object that we're shooting towards this comet needs to be roughly 1.3 million kilometers per hour, which is simply not feasible. And therefore we conclude that if it is only possible to shoot an object which has the mass of 0.1% the mass of the comet, then we will simply need to have a velocity that is not possible. So there's several things to do. Either we increase this angle of 60 degrees or we increase this mass. And if that's not possible, well, then we're simply doomed. And this brings us to the end of this video, and I hope that you're now more familiar with solving two-dimensional momentum problems. If you have any questions, leave a comment down below, and with that I thank you for watching, and I will see you in the next one. Bye.